Welcome to this explainer. Okay, today we are going to explore the totally hidden superhighway that powers, well, pretty much every single aspect of our modern digital lives. We live in this wireless age, right? We're streaming movies, we game, we make video calls, and it all feels like it's just floating through thin air. But the reality? The vast majority of our digital world relies on this massive, totally physical network of incredible technology right under our feet and even at the very bottom of our oceans. So get ready, because we are going to demystify fiber optics and trace the absolute incredible journey of light.
To kick things off, I actually want you to think about a really simple question. How exactly does a high-def video travel all the way across the world right to your device? We literally do this dozens of times a day without even a second thought. You click a thumbnail and boom, it instantly starts playing. But how does that data actually get to you? It's not magic, it's a physical reality. And to truly understand that reality, we kind of have to rethink how we send messages in the first place.
Picture this. Imagine you've got a friend who lives really far away, and you desperately need to send them a message. Now, you could try shouting, using sound, but let's be honest, that sound is going to fade away into nothing pretty fast. But what if, instead, you shine a super bright flashlight down a really long tube? Now you're using light, and light can travel remarkably long distances. Fiber optics works entirely on this second idea. Instead of relying on a signal that fades out quickly, it harnesses the staggering, raw power of light.
So what exactly is this technology? Well, fiber optics is essentially a giant superhighway for light. Instead of sending electricity through a traditional clunky copper wire, it shoots light through a very thin strand of glass or plastic. This incredible technology uses those light pulses to transmit our internet, our phone calls, TV signals, and our online gaming at just blistering speeds. When we talk about fiber optics, we are literally talking about steering light across the globe.
Okay, let's dive right into Section 1, Anatomy of a Fiber Cable, looking inside the glass strand.
Because a fiber cable is way thinner than most people realize, let's actually break down how it's built from the inside out. Right at the very center is the core. This is pure glass, and it acts as the actual physical highway for the light. But light likes to scatter, right? That's where the clouding comes in. It wraps around the core like a tube of mirrors to continually bounce that light right back to the center. Then, to keep that incredibly delicate glass safe from moisture or scratches, it's wrapped in a protective coating. And finally, the whole shebang gets a tough outer jacket to shield the entire cable from the elements and from being pulled around.
Now, the physics magic trick that makes all of this actually work is this phenomenal concept called total internal reflection. Imagine taking that flashlight we talked about earlier, flicking it on, and pointing it directly into a glass tube. Instead of the light just shining right out through the sides, it hits that mirror like cladding we just learned about and keeps bouncing perfectly inside. It bounces back and forth, reflecting internally without ever escaping the tube. Because of total internal reflection, this light can travel for literally dozens of kilometers, perfectly contained within that tiny glass core.
Moving on to Section 2, translating light to data and the absolute magic of ones and zeros.
So, we know how the light gets trapped and stays inside the tube, but how on earth does bouncing light actually turn into a complex video game or a text message? It all boils down to a surprisingly simple concept. Everything you see online, and I mean every high-res image, every single website, is converted into microscopic, rapid-fire flashes of light. A light flashing on represents a 1. A light flashing off represents a 0. Those endless sequences of ones and zeros carry all the complex digital information in the world. It is quite literally a microscopic Morse code made out of light, flashing billions of times every single second. Mind-blowing, right?
And why is this so incredibly fast? Well, because a single fiber strand doesn't just have to carry one beam of light. It can actually carry many different colored beams of light at the exact same time, with each single beam carrying completely different data. Think of it like adding more lanes to a massive highway. More lanes mean more traffic can flow simultaneously without anything slowing down. By stacking these beams of light, fiber optic networks achieve speeds that were completely unimaginable just a few decades ago.
All right, Section 3, Fiber versus Copper, and the Legacy Network Upgrade.
To really appreciate this insane speed, we kind of have to compare it to the traditional copper cables that it's actively replacing. Copper uses electricity, and electricity naturally faces resistance. That makes it inherently slower and really only viable for shorter distances. Fiber, on the other hand, is using light, which allows data to travel incredibly fast over vast distances. Plus, while copper acts like a giant antenna for static and electrical interference, fiber is totally immune to all of that. Ultimately, fiber offers vastly higher bandwidth, meaning it can just carry astronomically more information all at once.
If that all feels a bit too technical, let's use a super simple analogy to put it into perspective. Just imagine a water pipe. A classic copper cable is like your garden variety small water pipe. It gets the job done, sure, but it can only carry a very limited amount of water at one time. A fiber optic cable, though, that's like a massive underground municipal pipeline. Except instead of water, it's carrying light, allowing an absolute torrential flow of information to pass through at incredible speeds. It's just a colossal upgrade in sheer capacity.
Which brings us to Section 4, types and splicing, and how we are actually connecting the world.
Now, there are two main types of fiber used to wire up our world. First, you have single-mode fiber. This uses highly powerful lasers shooting down a microscopic core, pushing signals well over 100 kilometers. This is the real heavy lifter for telecommunications and those major internet service providers. On the other hand, you've got multi-mode fiber. This has a slightly larger core, allowing multiple light paths to bounce through at once. It uses simpler LEDs instead of lasers and is absolutely perfect for shorter distances, like wiring up a massive data center or connecting buildings together on a college campus.
But here is a wild thought. What happens when one of these cables accidentally gets cut by a backhoe or just needs to be extended? You can't just strip the ends and twist them together like electrical wire, right? I mean, this glass is as thin and fragile as a human hair. Technicians literally have to splice them. The most precise way to do this is fusion splicing. A specialized machine perfectly aligns the broken ends and uses a localized electric arc to literally melt the two pieces of glass together into one continuous strand, resulting in virtually zero signal loss. The alternative is mechanical splicing, where the fibers are just very carefully aligned inside a small connector. It's definitely quicker, but it does introduce a bit more signal loss than melting them into one piece.
Okay, Section 5, the global footprint. Where is fiber actually used?
Let's zoom out and see how this all builds together. Where is fiber used? Basically everywhere. It's bringing fiber to the home for ultra-fast personal internet. It's the absolute backbone for huge, sprawling cloud data centers. Critical institutions that literally need zero latency, like hospitals, schools, and banks, they rely on it heavily. Even your wireless cell phone relies on it, because mobile towers use fiber for their main connections back to the network. And perhaps the most mind-blowing part? Massive bundles of these tiny glass threads form the giant undersea cables that cross our oceans, directly connecting entire continents together in milliseconds.
When you stack it all up side by side, it's pretty clear why fiber is the undisputed champion of modern communication. It gives us extremely fast internet speeds and huge bandwidth to carry enormous amounts of data. It works over incredibly long distances without the signal degrading. It is completely immune to random electromagnetic interference. It's also way more secure, because it's incredibly difficult to secretly tap into a light signal without being instantly detected by a drop in the light level. And practically speaking, it's super lightweight and much thinner than those old, heavy legacy copper cables.
But to be perfectly objective here, upgrading the entire world isn't entirely easy, and it certainly isn't cheap. Fiber optics require a massive initial financial investment to dig up roads and install. Also, unlike rugged copper wire that you can just throw around, we are dealing with fragile glass that requires extreme care and delicate handling. And as we just saw with the fusion splicing, installation and repair require highly specialized, very expensive tools and extensively trained technicians. You can't just hire a standard electrician to go out and fix a microscopic glass highway.
So to wrap up our explainer today, your absolute key takeaway is this. Fiber optics is a technology that takes our digital information and sends it as pulses of light through incredibly thin strands of glass. Because light travels so ridiculously fast and can carry enormous amounts of data at once, it provides the fastest, most reliable communication systems we have on Earth today. It is a literal superhighway of light running right beneath our feet. Which leaves us with this final thought. Since we have successfully harnessed light to connect entire continents in mere milliseconds, what new digital frontiers is the superhighway going to unlock for us next? Thank you so much for exploring the journey of light with me today.